Hello, everybody. Hello, 4 persons joining me.
And participants, on behalf of the Shaw Prize Foundation, to the Shaw IAU workshop on astronomy for education.
Hello, people who are listening at this point already. As probably a number of you know, we currently have global internet infrastructure problems, notably with Cloudflare. So this is the emergency replacement session for the second opening of the Shaw IU workshop on astronomy for education, which was supposed to take part starting 10 minutes ago, but the event platform crashed. Hi, Deborah. We
Hi.
are already visible. Just waiting for people to come over and trying to get everything working in the background. I think there's currently 16 people. So YouTube does not seem to be affected at this point, although that means that we're losing our Chinese colleagues at this point because they can't access YouTube. But I think we will need to make sure that, and we're going to give people some time.
Is this being recorded so that they can watch it later?
Oh yes, this is. I'm recording this. And I'm just trying to get everything in place. All right, still 13 people. That's not a lot. I'm going to ask. I mean, getting people to join is going to be a problem depending on how easy it is to reach them.
Of course.
I'm sending an email to OAE staff for just that. And while we are okay, now Cloudflare is announcing they've found the problem and the fix is being implemented, but don't really have a time scale for that, do we? So let's stick with this plan B. All right, for the 13 people who are already here, let's at least give them some something for their non-money, since all of this is for free. Can you share some reminiscences from the early times of the OAE? Because, I mean, do I recall correctly, you were also deeply involved in the strategic plan 2020-2030?
Yes. Oh, absolutely. Yeah, we're so excited to have Marcus take charge to head the Office of Astronomy for Education, because it seemed like a very important part of the mission of the IAU. So we're all thrilled by your work and the work of all of your many team members, both in Heidelberg and around the world. And it's just been remarkable how you've carried on these workshops for so many years now, touching so many people. So despite a problem that's not your fault today with Cloudflare, I'm very excited for the 7th workshop to be underway, and I hope it goes smoothly from here on out. I just want to thank you on behalf of the IAU leadership for all the work you've done over the years.
Sure, thank you, and I'm glad to hear that. So we're getting in the comments, we're getting a comment from Astro for EDU that they're trying to retrieve the email list to send the link to everyone. So presumably people will be coming in once we have managed to do this. And I see that some of the participants here are actually, because this is now on the HDA YouTube channel, so some of the participants here are the ones that usually come to our Monday evening live stream, which is in German. All right, so for anybody joining us, I'm here with Deborah Almagreen, an expert in galaxy research, but also an old hand at the highest levels of the IAU, former IAU president, and we are currently trying to wait for more people. We're having a pretty big online conference on another platform, but that other platform was affected by the international worldwide Cloudflare outage. Looks like YouTube is not affected, so fingers crossed. This was our first go-to solution, and let's see how we proceed. I believe in the background, the staff of the IAU Office of Astronomy for Education is very busy trying to get an email with the link to everybody who was supposed to join this, all the participants of the Shaw IAU workshop. So that is, for anybody joining us, this is why we are suddenly here on this channel. So I'm curious. Tell me a little bit more. Tell me a little bit more about. So whose idea was it to? Is the strategic plans, that is something comparatively new, right? I mean, we had one 2010 to.
Right. So
the first one.
Right. The previous strategic plan really started the Office of Astronomy for Development. So that was all focused on the OAD. And so that started the offices for the IAU. And Evine van Dieschek, the past president before me, and I decided we needed to have a strategic plan that would encompass all activities of the IAU. We thought the OAD was a wonderful start, and we needed to expand to other efforts. Of course, we had the Office of Astronomy for Outreach, and so we had for many years the Office for Young Astronomers, and that operated somewhat separately, and we folded it into the IAU family. And so we really thought that education was a component that was missing. So when we were developing the strategic plan, it seemed like that was critical. Teresa Lago was the general secretary at the time, and she played a big hand in pushing for an Office of Astronomy for Education. And of course, we had a process of many wonderful proposals from around the world to host it. And Marcus, you and your team came in as the one to lead the way. So it was, yeah, so it was is part of what we see as a core mission for the IAU to bring astronomy to the world in many different facets. So not just in outreach, not just in training astronomers and young astronomers, but in using astronomy as a tool for education, because of course it's so exciting for everyone to think about astronomy, and young people in particular get excited about it. And so it's a gateway into STEM studies. And so it seemed like this was what we really ought to be doing. And so you've carried that forward for us.
Can you pinpoint whose idea it was, or was it something that sort of emerged during the discussion?
It was part of a long discussion, but I'd say Teresa Lago was probably the one pushing it the most.
Okay. Well, she was certainly the ones that basically helped us start over and get going back in 2020, when we had global problems.
Yes.
On a rather different scale,
right,
than the outage we're experiencing right now. We have posted the message on Basecamp now, so all the NIACs should be in there. Apparently the only way to email all the participants is from inside the other platform, so they might have to wait for a brief window when the other platform comes along again. So I think numbers are growing very slowly, so I think the NIACs have not yet checked Basecamp. Let me just briefly request that we send this out to all the mailing lists we have. Let's see if the numbers continue to grow. So my own contact with the IAU previously to applying to host the OAE was also mostly via OAD, and also via what I think back then it wasn't even Commission C1, it was sort of the previous incarnation before it came to be Commission C1 and C2 for education and outreach. So a personal question for you. I mean, you are. It's not like as an astronomy professor in your case. There is. I'm not going to say that. No, I'm saying this wrong. But I mean, it's certainly not. It's certainly not a standard career move to really put in that much time and that much effort in an international organization like the IAU. So, what motivated you to be active on that level?
Fundamentally, astronomy is for everyone, and it's been really important to me throughout my career to make sure that everyone gets that message, that anyone can enjoy astronomy, anyone can do astronomy who really wants to. That is, astronomy as a professional astronomer, but beyond that, it's just something that's part of our very core existence. And so I think that message has always been important to me to communicate to my students. But beyond that, I was president, before the IAU, I was president of the American Astronomical Society. And of course, we were very involved in education and outreach efforts there as well. And so it seemed like a wonderful step for me personally to go from the American focus to the international focus. I mean, how great is this that we have a platform for reaching everyone?
And I mean, I'm assuming that almost nobody out there knows about the inner workings of how somebody joins the IAU at this high level. But I mean, from the fly on the wall position that I have now with the office, it looks like that the standard thing is that you first sort of join the executive committee, then sort of maybe make your way up to one of the vice presidencies, and then somebody
So,
from that pool will become president, or
so not quite. It is true that many of the presidents have been vice presidents. The executive committee consists of 6 vice presidents plus the 4 officers who are the president-elect, the general secretary, and the assistant general secretary. So many of those 4, what are called officers, vice presidents, are the executive committee along with them. Many of them were vice presidents, including me. But when the nomination committee proposes candidates, they look to people who have had service, leadership experience at some level. And so we draw on the national members, who are the countries who join through their national academies or their astronomical societies, to propose worthy candidates. And then they're thoroughly vetted. And so the selection committee comes up with a list of potential people and then votes on them to put forward. A lot of the leadership comes from early experience. So if you want to get involved in the IAU at a leadership level, the easiest way, you become a member of the IAU, which the applications are open now through December 15th. And on the IAU website, you can see a link to get to the membership application for your particular country. Those are decided and voted on by the membership committee and then the executive committee in the spring, and then you become a member. When you're a member, you join one of the 9 divisions, and you can also join any of the several dozen commissions and working groups in your specialty. So if you really want to be involved in leadership, the best way is to start off by proposing a working group or joining a working group, becoming a leader of a new working group that's proposed every 3 years at the General Assembly. Become a commission leader. From the commission leader, you might run for division president or secretary. And so often those division leaders become vice presidents later, because they're people who have proven that they care about the IAU, they understand its workings, and they've got proven leadership ability. So you don't have to be a leader within the IAU to become a vice president or president or general secretary, but you need some evidence that you're willing to do service, because it is quite a lot of work, and it's all volunteer among the executive committee and officers, as well as the divisions and commissions and working groups. But you have to want to do that. You have to want to do service, that is, help astronomy with other people, and get known for being someone willing to put in the work.
Yeah, I mean, it's a little bit of a contrast with the way that the usual scientific career system works. And correct me if I'm being too cynical here, but my impression is that at least for a long time, science careers really depended on your research output, and there was not a lot of thought given to the fact that if you are the leader of a research group or even of an institute, then there's additional qualities that you need and that do not necessarily correlate with putting out really good research articles. And a number of people have been on the receiving end of this discrepancy. I'm being very diplomatic here. So what I like about the IAU system is that you can see the qualities that you need later on. You can actually see them throughout the career, and it's not that the person with the best research becomes president. It's really more tailored to the job that they're actually meant to do, which is herding cats, right?
That's right. And drinking from the fire hose. I think that to a lot of young people out there who may be in academic careers or in other areas of astronomy, often you're called upon to do service, and often mentors advise younger people not to be involved in too much service. Concentrate on your research so you can get ahead. It depends on what your goal is. So for me, I always said, yes, you want to be on this committee to review this little bunch of proposals. Sure. And then people saw that I was willing to do that. So then they'd step along. Oh, would you like to be on this bigger committee, on this bigger committee? So I think that it does take an awful lot of work. And but it depends on if it's worth it to you. To me, it was always worth it. My research was extremely important. I think I was at a small college for 37 years. It didn't have a graduate program. And so my outlook probably was a little different from a lot of astronomers who are at a big research university with postdocs and grad students, which we didn't have. But for me, it was all about the undergraduates. And then it was about serving the college on many different committees because I thought that was an important community. And so it was a logical extension to go from there to the astronomical community within America and so on. So I think service takes a lot of work, and it's not for everyone, but to me, it just was important. So I think if this sort of thing appeals to you, then you should find ways to get involved. And so if you're asked to referee a paper, you're asked to serve on a small panel, you're asked then to serve on a review committee, all these things are stepping stones to providing you with qualities that you need to be a leader. So keep that in mind. If someone asks you to do something, you decide if it's important to your career and also if it fulfills you. And for me, service is a very important part of what my career has been about.
But there is the practical aspect of needing to find a permanent position. First, I
Right.
hesitate to say first because people can start earlier, but the people that you mentioned to say concentrate on your research, I think
Yeah.
what they do have in mind is that do the research because that's what you need to find a permanent position. And I actually think it's better in the US where there's sort of smaller colleges and a wider diversity of conditions.
Right.
In Germany, it's basically chairs and Max Planck directorships and not much else that's really permanent. I'm exaggerating slightly here, but it is a problem.
It is a problem. Certainly, it's difficult when there are many, many years worth of past the PhD, then what? And maybe one or two or even three postdocs these days. And with funding uncertain everywhere, but I'm from the US, obviously difficulties right now.
Condolences.
Yes, it's a tricky time, both globally and at that stage of one's career. So certainly you need to get the research underway in order to be recognized as an astronomer. And yeah, that can take many different forms. It's also true that you don't need to be in academia or at a research institute. You could be at a space science related industry. In the US, I would say NASA is a prime example, but again, NASA's
not a good example at this time.
Not a good example at this time. But yeah, so I think it's difficult.
Yeah, let's not go there.
Yes, let's not go there. In terms of careers, I think the important point is to remember that what you're learning in your studies as an astronomer can be applicable to such a wide range of fields. And certainly if we go the route of, oh yes, learn all about computers, certainly you will have a good foot in the marketplace with computer capabilities. I think that's not going away.
Oh, yes, I think, and that's a whole other discussion with generative AI. But yes, so at least in a society that values itself, we are assuming that these kinds of skills should always get you
right
towards.
Basically, learning how to think, I think, is critically important.
Yeah, it is, and the impression is that it's getting more important and more important, and also my impression is, I'm looking at Germany, at the US, but my impression is that lots of I'm not saying lazy shortcuts, but let's say lots of the shortcuts are not up to the new environment where some sources just spout falsehoods, and so all the things that all the habits and all the customs that basically rely on all the actors be acting at least to a certain degree in good faith. And I think that's true within science, where sort of there's an onslaught of AI-generated articles at the journals, but also, of course, society in general. So all these shortcuts that we've lived with for the past years suddenly require rethinking
Yes,
somehow.
absolutely. Yeah.
I don't think that's. I mean, obviously, currently the number of consequences of what's going on there are horrific, but I actually think that it's an opportunity to think about why do we trust certain sources? What are the scientific habits, such as citing your references, making your arguments transparent, and so on. So I think that sort of it does force us to go back to the bedrock that was always there for at least for as far as science is concerned. And so yeah, I think that's
Right.
an interesting area of development if we get the chance to evolve in that direction.
Which is why I think a workshop like this can be so important for elementary school and high school teachers to instill in students the value of the scientific method. What is this all about? It's not, I think this is happening. No, I think this is happening. No, that there are true arguments that can be tested, and you refine your theory if they don't match data, that it's driven by evidence. It's not just people thinking of things randomly and thinking, I believe this. It's not about beliefs. It's about being able to lay out a process. So I think that this kind of workshop is exactly where we need to start. Not the workshop per se, but just at the very young level, to let very young people understand what's going on.
That's actually something that I've been thinking about for a while now, because we've always had in the background, our motto was always that astronomy is a gateway science to the wider area of STEM. But as far, I mean, other sciences that use statistics, for instance, are also linked with the bridges of mathematics, if you will.
Yeah.
So I think I mean, as you know, for this year's Shaw IU workshop, if it gets off the ground in spite of the infrastructure trouble, we have authentic astronomical data as one of the themes, and I think that is a very promising direction to take, and it is a very direct way of using astronomy to really open up a wider field of applications that are essential in all fields, if you want to make sure that you're arguing that you're building the kind of consensus that you cannot build with belief or ideology, but that in principle, if you do it right, you should be able to build with data, with the proper treatment of the uncertainties, and with actually trying to lay out which are the statements that we can all agree on based on certain standards of judging evidence. So
Yeah, absolutely. I think that's one of the beauties of astronomy, is that when we have these really expensive missions that are international efforts, the data are available to everyone. And so just having the training to learn how to manipulate large data sets, how beautiful is that? That you don't need to just look at a James Webb image and say, isn't that pretty? You can actually download the image and work with it. And so I think that that's a very powerful message.
for a given definition of working with it, because the first thing that you learn, I mean, the first thing I learned the first time I actually looked at real raw Hubble data is that it is so different from it is sort of pockmarked with cosmic ray particles.
Right, right.
It is it does show you something about the engine room behind all the pretty astronomical pictures.
How the
Um,
sausage is made.
I Yes and no, because I mean it's not ugly. I don't think people who want to see how the sausage are made. I don't think that you can get most of them to appreciate I don't know, the beauty of what's going on there. But I think you can make people appreciate the beauty of raw data and the fact
Oh
that
yeah.
there is a process that gets us from one to the other. And key difference to sausages is that this is the best data where all the money is invested, where all the we have sort of the best conditions out in space. So I think that's, yeah, I see your point, but and I see I'm getting sidetracked. But I completely agree about the role of astronomy also for another reason, because in the end, where we as societies, regardless of which country we are in, need to discuss data and evidence and arguments is oftentimes highly controversial political issues. So
Oh,
if you
yes.
start explaining methodology using those issues, then people are going to have their preconceptions depending on which side they're on. So I find the idea quite attractive of saying, okay, astronomy is fairly uncontroversial. Maybe not totally uncontroversial, but most of us can really agree on, yes, this is what it is, and
Yeah.
regardless of what our general worldview might be. So I think
Yes.
that's really a big plus. So
Yes.
we are going to move in that direction over the next years, and I'm very interested in that. I think so. We have now 42 listeners, including, I think by now, a number of people from the original session. So I'll just gently pull you off the stage, Deborah, and
Yes.
we'll start with we're now 38 minutes late, but we'll start with the opening of the Shaw IAU workshop. I'll see you in a bit.
Thank
All right. So welcome to everybody who is already here. Welcome to anybody seeing this as a recording. As you know, internet infrastructure problems are the reason why we are currently not on our usual event platform for the 7th Shaw IAU workshop on astronomy for education. Instead, we are here on StreamYard, hosted by Haus der Astronomie at the Max Planck Institute for Astronomy. This is the channel that we usually use for our outreach live streams every Monday. So I think some of the people who do join us Monday evenings German time are also here, because this is streaming automatically in the Haus der Astronomie YouTube channel. So, but what we are really here for right now is to open the 7th Shaw IAU workshop on astronomy for education. It's the second opening because one of the principles of accessibility of this workshop is that we try to do all the events in 2 different time zones at 2 different times. So regardless of where you are on the globe, you will be able to join us at hopefully at one of these times. And this is in fact the last Shaw IAU workshop under this particular name. This is the last one that is in partnership with the Shaw Prize Foundation. The Shaw Prize Foundation has very generously supported these workshops, actually starting in December 2019 until 2025. And they're a joint venture, if you will, between the Shaw Prize Foundation, the International Astronomical Union, IAU, and the Office of Astronomy for Education of the IAU, which is housed by Haus der Astronomie and at the Max Planck Institute for Astronomy in Heidelberg. So welcome everybody who found their way here. We've tried to email everybody whose address we had. We've tried to use all the mailing lists. We have a trouble getting at the registered participants because we have trouble getting on the event platform, but hopefully people are going to find their way here. And at this point, I'd like to hand over, at least virtually, to the president of the International Astronomical Union, Willy Benz, who has sent us a video of greeting.
Greetings, everyone, and welcome to the online Shaw Prize Foundation IAU workshop on astronomy for education. My name is Willy Benz, and I'm the president of the International Astronomical Union. I am delighted to welcome you all today to this exciting event. This event marks the end of the Shaw Prize Foundation's generous support for this workshop series. The very first IAU Shaw workshop took the form of an in-person meeting in Paris in December 2019. On that occasion, an extensive stakeholder community discussion was held to launch our brand new Office of Astronomy for Education. All of the following 6 workshops were held online, with the last one in 2024 attracting 740 participants from 90 countries. Between 2023 and 2025, the Shaw Prize Foundation also enabled an additional 6 regional workshops to be organized, where educators and astronomers from specific geographical regions could meet in person. These workshops took place in South Africa, Turkey, Nepal, Panama, Argentina, and Egypt. We are extremely grateful to the Shaw Prize Foundation for their generous support over all these years. Thanks to this support, we have been able to reach and help an incredible number of educators and teachers, who in turn have reached an even greater number of school children and students. In addition to the usual topics of astronomy education, teaching methods, and research in astronomy education, this 7th workshop will have a special focus on teaching with real astronomical data, as well as a scientific focus on galaxies. As with everything the IAU does, nothing would be possible without the enthusiastic help of the community. I would particularly like to acknowledge the tremendous effort of all the National Astronomy Education coordinators. Currently, we have 345 NIACs stationed in 150 countries, who play a vital role in enabling the IAU to engage with various communities and territories worldwide. What makes us absolutely unique is this global network and the fact that the IAU can count on so many knowledgeable and engaged people worldwide. We are unique not just in terms of our capacity, but also in terms of our actual global impact. I would like to convey the message that your work is immensely appreciated and recognized as a vital contribution to the IAU. I would like to end by wishing everyone an exciting and productive workshop full of discussions and exchanges. Thank you very much.
So thank you to Willy Benz as the current IAU president for his kind words. And next we will have Kenneth Young representing the Shaw Prize Foundation, our major funders this year and the previous years. So let's see, I hope this works.
Organizers and participants, on behalf of the Shaw Prize Foundation, I welcome you to the Shaw IAU workshop on astronomy for education, the 7th in which the Shaw Prize Foundation has partnered with IAU. The workshop is put together with the energetic effort of the IAU Office of Astronomy for Education, OAE. I especially want to salute Dr. Willy Benz, President of IAU, Dr. Marcus Purcell, Director of OAE, Dr. Carolyn Lifka, Deputy Director of OAE, and also the National Outreach Coordinators, over 300 volunteers who help to connect the astronomy education communities in over 100 countries and territories worldwide. Astronomy is one of 3 prizes offered by the Shaw Prize Foundation. The Shaw Prize was established under the auspices of Mr. Run Shaw in the year 2002 and has been awarded annually since 2004, 21 years ago. The Shaw Prize Awards, made without regard to race, nationality, gender, and religious belief, are dedicated to furthering societal progress, enhancing quality of life, and enriching humanity's spiritual civilization. Goals that resonate with IAU and with the Initiative on Astronomy for Education. The stars, the galaxies, and the cosmos are objects of great interest to young people and magnets that draw.
I'm sorry, that seems to have been too much for my connection, trying to upload both the video by Kenneth Young and in the background the one by Deborah Almagreen. Could someone in the comments please tell me, was the video from Kenneth Young, was that did he get to finish before the work issues came along, or are there parts missing? Okay, Deborah is telling me it cut off and he was also frozen. All right, let's try to do at least the final part a little bit differently, with me playing it locally on the computer, so not needing to upload this per se. Shaw Prize Foundation. That looks good. It's a very high quality video, and that is currently adding to the difficulty because of size. So I'm going to now try it this way. Yep. Put in here. Then I do think we had the first part. I think this might be hopefully where it cut off earlier on.
Objects of great interest to young people and magnets that draw them into an intellectual world driven by curiosity and unbridled imagination. But astronomy is not just imagination. It must be firmly rooted in empiricism and rationality. I am therefore especially pleased that the theme this year is teaching with authentic astronomical data. The internet and affordable computing are bringing young people around the world into contact with the frontiers of astronomical exploration. and narrowing the divide between beginners and professional researchers. The online format since the second workshop in the year 2020 has expanded outreach. I believe there are close to 800 participants, and through you, tens of thousands will benefit from being brought closer to real observations. The workshop will fuel the enthusiasm of young people on whom further advances in astronomy and in science rely. We wish you the best for the workshop. Indeed, nothing would please us more than if these endeavors would inspire young people who, say, 20, 30, or 40 years from now, were to contribute to major advances and win Shaw Prizes in astronomy. Thank you.
Okay, let me just sort of doing everything by hand here, not quite as planned. So those were the words from the Shaw Prize Foundation, who is financing the infrastructure, the infrastructure we had originally been on in this online workshop. Hopefully, the infrastructure that will continue working, or that will start working again shortly, so we can continue. But right now we are here on StreamYard live streaming on YouTube, and as was already mentioned, our science topic this year is actually galaxies. So we are very happy that we have here with us. Also going to ask her on the stage later on, but right now we have sort of a recorded keynote speech. We have with us Deborah Almagreen as an expert on galaxy, but also the author of a popular introductory textbook on galaxies and galaxy structures. So this is to kick off the science part of our workshop. Part of what we do aim to do these workshops is to help teachers keep up with scientific developments. So now let me see how I can start this in the present slightly improvised environment. And let me just
Hello, I'm delighted to join you all for this second opening session.
Oops, so sorry, let me just share this, and then we can start.
Session for the 7th annual Shaw IAU workshop. I've been invited to give you an overview of galaxies to serve as a background for some of the more in-depth talks you'll hear in the galaxy session later on. So let me share my slides. Astronomy, as you know, is the oldest science. It inspires and unites us. And yet it's only been 100 years since astronomers have had telescopes big enough and techniques clever enough to figure out that there are other galaxies. We estimate that there are over 100 billion galaxies. So what is a galaxy? Galaxies are objects that contain between 1 billion and 1 trillion stars, plus gas, dust, and dark matter, all bound by their own gravity. In the nearby universe, 3 main shapes prevail. There are ellipticals, which have 3-dimensional shapes, like giant balls, and they are red. Spiral galaxies are flattened. They're like giant frisbees with a central bulge, and they have spiral arms and a pinwheel pattern. The arms are very blue because of new star formation. Because spiral galaxies are thin, seen from the edge, they have this appearance, with the central bulge and the main disk. Irregular galaxies are chaotic and are quite blue because of new star formation. They tend to be between a tenth and a hundredth the mass of typical spiral galaxies, although they span the low-end range for elliptical galaxies. Edwin Hubble, 100 years ago, was studying different shapes of galaxies, and he put them together in what's known as the Hubble tuning fork. This is not an evolutionary sequence, but just a sequence to separate out different shapes, much as we do when we're looking at different kinds of plants and animals, and we sort them into categories according to their similarities and differences. With galaxies, when we divide them into their different shapes and colors, we're actually probing the underlying physics. Galaxy shapes reflect how the stars are moving. In elliptical galaxies, the stars are orbiting about a common center of mass, but the orbits of the stars are random, and so they fill a three-dimensional volume, and that gives us the round shape. When we look at spirals, they have rotational motions that dominate the random motions, and so they're flattened to a disk. The motions are typically 100, 200, 300 kilometers per second in the disk compared to the random motions of the stars and gas, which are in the ballpark of 5 to 10 kilometers per second. So we have here ellipticals that are round and red. When we look at the spirals, they're flattened and with a pinwheel structure. They have blue colors, which reflects their star formation histories, as I'll talk more about a little bit later. Here are elliptical galaxies. They all look very similar. Some of them are a little more flattened than others, but they have very little gas today, and that's why they can't make new stars. So what we're just seeing are old low-mass stars, which are red. Spiral galaxies are rotating in a plane. They have the right conditions for waves to ripple through the disk and generate the pinwheel pattern. Because they have a high fraction of gas, that leads to new star formation. So we see arms that are quite blue, filled with hot, high-mass stars. Our Milky Way is a spiral galaxy. Its total mass is estimated to be about 200 billion times the mass of our sun. Gaia is a satellite that recently released data on 200 billion stars. So this is a visualization of that data set. If we were to fly over our galaxy, we would see that the central region has an elongation called a bar with many spiral arms, and we live about halfway out in the disk, right here in what's labeled the Orion arm or the Orion spur. When we look at the night sky, if we're in good seeing conditions, we can see that band that we call the Milky Way. But that's the name of our whole galaxy. In fact, the Milky Way is the plane of our galaxy. On the left is a spiral galaxy seen from the edge, and you can see it looks a lot like our view of the Milky Way. Now, because we're sitting in a disk which has some extent, imagine we're in this galaxy halfway out, and we look around us and we see stars everywhere with the blackened region in the middle. That's what we're seeing here, where we have nearby stars and the disk of our galaxy. The dark regions are where we have gas and dust mixed together. The dust is blocking starlight, so it appears black. If we look at a close-up of some regions in our galaxy, here's a little star cluster. This is a molecular cloud. The cloud was once much bigger, and part of the gas went into making this star cluster. Stars often form in clusters, and today when they form in what are called open clusters. This is the Pleiades, the center of it, which actually contains 1,000 stars. And open clusters tend to be rather blue because they have some high-mass stars that have recently formed. Globular clusters are the oldest unit in our galaxy. They contain hundreds of thousands of stars. And because of this high mass, they're able to maintain a spherical shape rather than the distorted shape of a typical open cluster. This is a picture from the Webb telescope where we see a star cluster that has formed. It's cleared out the gas around it to make the stars, so we see a little cavity, and we see with the Webb telescope some of the hot gas, which is caused by ionization from the high-mass stars. Regular galaxies are fluffy disks. They're rotating, very slowly rotating, less than 100 kilometers per second. But they have a very high fraction of gas, and that leads to new star formation. The high mass stars appear quite blue, but sometimes the gas is near the hot stars and it gets ionized, and so it appears as red. Galaxies provide insights into the conditions in their universe. How and when do they form, and how do they evolve? The clues we have to study them come from looking at them through electromagnetic radiation, from gravitational effects, let's see how they interact with their neighbors, and through computer simulations, where if we think we know the physics, we can put together a model of how an individual galaxy is evolving or how the universe on a larger scale is evolving. So we can compare those simulations with the observations and see if they match what we're seeing. If not, then the parameters can be adjusted to give a better representation. Galaxy light is composite light from all the billions of stars that make it up. So to interpret galaxy light, we need to know the color and brightness of a star as a function of its age and mass, the lifetime of a star of a given mass, and the relative proportion of stars of different masses. And we can do this by looking at stars in their own galaxy. Then a galaxy's color and brightness can be modeled to determine its star formation history and its mass. Stars have colors that depend on their surface temperatures. This is a plot of brightness as a function of wavelength, and we can see that stars to first order are blackbody emitters. We have a radiation that peaks at a characteristic wavelength that depends on the temperature. So for blackbody radiation, we have a peak wavelength that's a constant divided by the surface temperature of the star. Our sun has a surface temperature of 6,000 degrees, so it appears yellow. That's right about here on this plot. If we look at a hotter star, then we see it peaks at shorter wavelengths. And if we see a redder star, it has a cooler surface temperature. So hotter stars are bluer than cooler stars. This is Orion. You recognize the main stars and the belt and the sword. Betelgeuse is a red supergiant. It's red because its surface temperature is 3,000 degrees. Rigel is a blue supergiant. It's blue because its surface temperature is 30,000 degrees. We can also look at spectra of stars. Their absorption lines tell us their composition and their temperature. Here we see the spectra for hydrogen lines. So they have characteristic lines representing different transition of electrons in orbit around the nucleus. And we can see that the lines are more prominent at some temperatures than at others. So we have how strong the lines are as a representation of the surface of the star. We can also look in more detail. Here's a spectrum with many different lines for different elements. And so we can get an indication of what elements are present in the atmosphere of a star. Stars are typically 90% helium and 90% hydrogen, 9% helium, and less than 1% of heavier elements. But these heavier elements tell an interesting story because initially in the universe we have primarily hydrogen, and we build up to just a few of the lightest elements, but any of the other heavier elements were formed in the cores of stars through nuclear synthesis. So as we have high mass stars form and evolve and process heavier elements, they explode as supernovae, and the heavier elements are dumped into the surrounding gas so that new stars are born with those heavier elements already in their outer layers. So when we see different elements in the outer layers of a star, then that tells us something about what preceded that particular star. So we get something about the star formation history. A star's luminosity depends on its size and temperature. So here we have several stars. Here's the sun. Here's Arcturus, which is a giant, but there are also supergiants, and Arcturus looks very tiny next to Betelgeuse. And although Rigel is a supergiant, it looks tiny also compared to Betelgeuse and Antares. This is the iconic Hertzsprung-Russell diagram that plots the luminosity of a star as a function of its surface temperature. There's a lot of information here. The main sequence is where the stars spend 90% of their lifetimes. That's where they're fusing hydrogen to helium in the core. Once that process is complete, they evolve off of this main sequence and become giants if they're low-mass stars, or supergiants if they're higher-mass stars. Now look at these masses. We see that up here we have stars that are 10 times the mass of the sun or higher. Here we have the sun, and here we have stars that are lower mass, a tenth of the mass of the sun. The lower mass stars we can see are quite red because they're cooler, and the high mass stars are much hotter on the surface, and so they appear bluer. So we can see from this diagram why ellipticals are red. We have high mass stars that only live a short time, a lifetime of 10 million years. We look at the sun with 10 billion years, and lower mass stars with tens of billions of years. So if ellipticals are not making new stars, all the high mass stars have already evolved off and we no longer see them. And so we only have the low mass stars, which are quite red. But spirals are making a lot of new stars all the time, a few stars per year typically. And so we always have a same relative proportion of high and low mass stars. Every time you throw in some high mass stars, they're very luminous, and so they're going to dominate the light. And so we see blue light because they're hot. So when we're looking at galaxies, we can use filters to highlight the different features. Here we have the electromagnetic spectrum from the gamma rays, very high energy, to the visible light. It's most of what stars emit, to the longer wavelengths where we're probing dust and gas. So here we have X-ray. This is all the same galaxy. In X-ray, we see high energy emission from supernovae, high mass stars that have exploded. In the ultraviolet, we have the emission from the hot young stars. In the visible, two different stretches of the same thing, we're looking at stars typically a few times the mass of the sun that emit primarily in the visible wavelengths. At 3.6 microns, we're looking in the infrared at the cooler, older stars. That is, the ones that live longer. When we go to 8 microns and 24 microns, we're probing the dust in a galaxy. Dust, like polycyclic aromatic hydrocarbons, is heated up by the high mass stars. And so we see the gas and dust that are mixed with the rest of the disk, or the dust is showing up because of the presence of the high mass stars. So it's also following a spiral structure. And in 21 centimeter, we're looking at the atomic hydrogen in the galaxy. So in all cases here, we're seeing a spiral structure, but we see a lot of different details depending on what component we're observing. We can also use spectroscopy to dissect the light. Here's a picture of a spectrum. And if we plot the brightness as a function of wavelength, do a scan across the spectrum, then we can see these absorption lines, and we can get the relative abundances of different elements by looking at the areas under these curves here. So a galaxy spectrum is showing composite starlight of the billions of stars that make it up. So here is a schematic for an elliptical galaxy, brightness as a function of wavelength. This is the red end, and elliptical galaxies, again, are dominated by the old low mass stars that are red. Whereas we go to spiral galaxies, and we see a peak towards the bluer end because of high mass stars. To analyze starlight from faint distant galaxies, we use satellites such as the Hubble Space Telescope, launched 35 years ago, and the James Webb Space Telescope, launched just 4 years ago. The Hubble telescope has a 2.4 meter mirror that's sensitive to ultraviolet and optical wavelengths. The James Webb mirror is 6.5 meters and is sensitive to infrared wavelengths. Here are two pictures of the spiral galaxy M51. On the left, we have the Hubble view of it. So we're looking at the optical, and we can see the stars. We can see the dust that's blocking starlight in the spiral arms. And on the right, we look in the infrared. The Spitzer Space Telescope was a precursor to the James Webb Space Telescope, a much smaller telescope. We can still see the following the spiral pattern from the dust that's been heated up by starlight. These are central images of M51 with a team that I'm on using James Webb Space Telescope. And in the top, we see the near infrared, where we're looking at emission from hydrogen gas, where the electrons have been stripped off from the high temperature stars, and then the electrons recombine and emit a red wavelength. So that's what we're seeing here, the so-called H2 regions. And at the bottom, we're looking in the mid-infrared, combination of 5 to 28 microns. And so we're seeing the embedded dust. And so as we look at these regions, we see regions where there are stars that are forming that are embedded in the dust. So in the optical, they haven't quite broken through. And we can see this tremendous complicated network within the disk of the galaxy. Here's another spiral galaxy. On the left is the Hubble image showing the starlight. You can see some H2 regions in the dust lanes. On the right, we're looking with the Webb telescope. And so we're looking at the infrared component, again, false color. And in the middle is the combined image. So look here where we have some regions that are black in the optical, and we see some star formation going on when we look in the infrared, and we see these cavities where regions have been cleared out by stars that have formed. Here's another spiral galaxy. This time we've added data from the Chandra X-ray satellite, shown in blue, and radio data for the gas, shown in pink, and the optical and infrared data from Hubble and James Webb, shown in the outskirts. So when we look at different filters, or in this case, use different telescopes sensitive to different wavelength regions, we can get a lot of information about the activity going on in a galaxy. Ground-based telescopes complement our space-based telescopes. We have a lot of 5 to 10 meter telescopes, and new ones are being built. The biggest one will be the European Extremely Large Telescope with a 39 meter mirror, and that's due to be completed in a couple of years. We also have the Vera Rubin Observatory, which is an 8.4 meter mirror. It's a very wide field camera, and it saw first light this past June. Here's the image, the very first image taken with the Rubin Observatory, and you can see tremendous detail in here with lots of different kinds of galaxies and stars in our galaxy. It's embarking on a 10-year survey where all the sky that it can see will be imaged every few days in different filters. So this will build up a very deep image and also lots of different kinds of objects. It will image overall about 20 billion galaxies, plus stars and solar system objects. Because the survey will repeat every few days, it will also observe transient objects, objects that are moving, such as comets, and objects that vary in brightness, such as supernovae. We use radio arrays to study gas atoms and molecules. Here's the Atacama Large Millimeter Array, also in Chile, like the Rubin Telescope, and it's looking at molecules. Molecular hydrogen does not radiate very strongly, so carbon monoxide, which is the next most abundant molecule, serves as a tracer for molecular gas, and it emits at millimeter wavelengths, and so this telescope array is good for high sensitivity, high resolution studies of galaxies. The Very Large Array in New Mexico is designed for 21 centimeter work primarily, which is looking at the neutral emission from hydrogen atoms. Here we have a montage of galaxies observed in hydrogen in false color. And to give you a sense of scale, on the left we have 2 galaxies where we've got a combination of optical and radio data. On the top here we have the spiral galaxy M33, which is nearby in our universe. And the optical part is just this very central part. The purplish regions on the outskirts, that's where all the atomic hydrogen shows up. It's in the interior as well, but it's all that exists in the outskirts. The gas there is too low density to form new stars, so it's just atomic gas. For M51, we have the optical part in the center, and all this blue is where the hydrogen extends, so we can see a long tidal tail from the interaction of these 2 galaxies with each other. Galaxies often have neighbors, which affect their evolution. This is looking at the central region of what's known as Stephan's quintet, with the Hubble on the left and Webb on the right. In Hubble, we can see, again, long streamers. These are stars that have been pulled out from the interactions of the galaxies. And in the infrared, we're highlighting some ionized gas from a shock as these galaxies are interacting, and they're creating new star formation. And when you have galaxies that are about equal mass that come near each other, they will, by gravity, eventually coalesce, and they create giant elliptical galaxies. Here's another view of a larger view of that group of galaxies. And here we have a radio image. The atomic gas is color-coded in red here, And this is observed with China's FAST radio telescope. And just to emphasize, the gas is coming from all of the individual galaxies, but it's been pulled out of them through their interaction. So it sits as a large envelope around them all. This is the very first simulation that was done of galaxies by the Toomray brothers in 1970. They were looking at this galaxy, which is really two galaxies merging, and they were intrigued by the long tidal tails. So here's a simulation in a series of time steps. Two spiral galaxies coming near each other, and as they get closer, the tidal effects kick in. That's where you have differential gravity, stronger when they're closer and less strong where they're further away, and that's what pulls out these tidal tails. And over a series of time steps, you see these long tidal arms developing. These galaxies will eventually merge as well. If we look in this green region here, the blow up shows a Hubble view where we have a rampant star formation from the gases that's been triggered to form new stars from the interaction. And as we look in the infrared on the bottom, where we see black in the top from dust obscuring starlight, on the bottom we have emission of the dust heated up by the stars. This is a pair of galaxies I've been studying for a long time. In the top, we have the Hubble optical image showing the stars. This little galaxy is behind this bigger galaxy, but they're orbiting each other. Here we have, with Spitzer, we see the infrared, and with the VLA, we're looking at the gas distribution. So this pair of galaxies is 120 million light years away, which is relatively nearby. Light year is the distance light travels in a year, or about 6 trillion miles. So these galaxies are eventually going to merge, and here's a simulation done 20 years ago to give the essence of the details. Eventually, they will coalesce, and as they merge, they will produce a giant elliptical galaxy. The timescales for these kinds of interactions are on the order of a couple billion years. Andromeda is our nearest big galaxy. It's 2.5 million light years away. Our galaxy is on a slow collision with Andromeda and will merge in something like 3 to 4 billion years. Here's a simulation of the merger sequence. Here's Andromeda. Here's our Milky Way. Andromeda's getting closer and closer, and that will disrupt the gas in the galaxies to create new star formation. A lot of dramatic, violent events will occur, and eventually the two centers of our galaxy will merge, and we'll be living in a giant elliptical galaxy. Now, the sun will not be affected by this. Stars and galaxies are separated typically by pennies separated by city blocks, so they just move past each other, but it's the gas that's going to be affected by this collision. The large and small Magellanic Clouds are nearby irregular galaxies. Here they are in the southern hemisphere, about 150,000 light years away. They're being shredded by our galaxy because they're only a tenth and a hundredth the mass of our galaxy. Our galaxy's gravity just pulls them apart. And as we'll see in one of the talks later, there are star streams across the sky. We can look at the spectral properties of individual stars and see that they came from these galaxies, not like some of the stars in the rest of our galaxy. And we see, in fact, star streams across the halo of our galaxy because the Milky Way has shredded a couple of dozen tiny galaxies. And this is true of other large galaxies as well. This shows a plot of 1 million galaxies. This was produced in 1977 from surveys. And what we see here is that galaxies are to first order everywhere in the universe, but in detail, there are some regions where there are more galaxies than others. So the darker regions are where we have more galaxies, and the lighter regions where we have fewer. And you see what's known as the bubble void structure. This looks like a big bubble here and another bubble and another bubble. It's as if we have a giant bubble bath and we've just made a two-dimensional cut through it. The sizes of these bubbles turn out to be related to how rapidly the universe expanded. This is a large-scale three-dimensional distribution of galaxies. Galaxies can be clumped into clusters of hundreds or thousands of galaxies, and those clusters can be clumped into superclusters, which may be upwards of 1 million galaxies. And again, you can imagine that we've got this bubble void structure across the universe. In fact, we've got a simulation Euclid is another satellite, and the consortium is trying to model on a very large scale what the universe looks like. It just released this simulation of 3.4 billion galaxies. This is a piece of the simulation to compare with new data that was released in September. So here we see this fantastic filamentary structure where we have bubbles and voids, but they're all connected by what's known as this cosmic web. And where we have more stuff, we eventually will grow galaxies. So here's a simulation looking at a piece of the universe where we have this cosmic web, and over time, these orange regions here are where we have higher density, and that's where we're going to make the galaxies. Dark matter is what initially clumps in the universe randomly, and it attracts normal matter. And so galaxies that form in the gravitational wells of this cosmic web form, and they have a large dark matter halo surrounding the optical part of each galaxy. And you'll hear a talk about dark matter in another galaxy session later. Here's another simulation, the illustrious simulation. You'll be hearing more about simulations too. This is a present-day universe looking at the dark matter density. Pink is where it's very prominent. As we go further and further away, that is back in time, it's not so dense yet. On the right, we see the gas density and a blow-up of this region. And so we're forming a cluster of galaxies. And if we look with higher resolution in the simulation, we're forming individual galaxies. So again, the trick is to make these simulations match what we're actually seeing to get the right objects that are forming at the right time compared to what we observed in the universe. So to understand how galaxies change over time, we need to look to the early universe. The universe is a time machine. As we look out in space, we look back in time. Light travels at 300,000 kilometers per second. Our sun is 93 million miles away, so its light takes about 8 minutes to reach us. Jupiter's light takes about a half hour to reach us, since it's 4 times further away. Light from our nearest star, Proxima Centauri, takes about 4.25 light years to reach us, since it's 4.25 light years away. For comparison, it takes light about 100,000 years to cross our galaxy. So if we're looking at the outskirts of our galaxy, we're looking at stars that are tens of thousands of years older than when the light left them. The Virgo cluster is our nearest cluster of galaxies. Here we're looking at just the center of a cluster that contains a couple thousand galaxies. This cluster is 65 million light years away. So when we look at the light today, it left those galaxies when dinosaurs were still walking the Earth. We can now observe galaxies billions of light years away. So by looking at lots of images of galaxies when they were young, that is, when they were very far away, and comparing with galaxies closer and closer to us, we can piece together how galaxies evolve, not individually, but collectively. The universe is expanding, so light from distant galaxies is redshifted. Here we have a plot of velocity versus distance to galaxies. And we can see that because the universe is expanding, galaxies are spreading apart. So those that are further away are moving faster away from us. If we look at their spectra, we can see this from shifted spectral lines. Here we have traces of hydrogen lines. And as the galaxy is very far away, those lines are going to be shifted to longer and longer wavelengths. Recall that we can measure velocities from a Doppler shift, which is when there's a change in wavelength because there's motion between the objects. So suppose we've got something that's emitting, say a star, and we've got 2 people, stars moving away from this person. So the light wavelengths take longer and longer to reach us. They're stretched out. So it appears to be redder than what was emitted. And for the person to whom the object is approaching, the wave crests are bunched together, and so the wavelengths are shorter, and so we see a blue shift. So Doppler shift is a blue shift if it's moving towards us, or red shift if it's moving away from us. So for small velocities like motions in our galaxy, the velocity divided by the speed of light is given by the change in wavelength compared to the emitted wavelength. In the universe, there's a relativistic correction for high velocities. Sound behaves the same way. If we have a car that's moving towards us or away from us, blaring its horn, then we'll hear a higher pitch as it moves towards us and a lower pitch as it moves away. Using these same ideas, we can measure distances to galaxies in terms of the redshifted spectral lines caused by the universe's expansion. So the redshift, Z, is defined in terms of the relative shifted wavelength. What we observe compared to what was emitted, or the rest wavelength, is equal to Z plus 1. So suppose we have a galaxy at Z equals 4, violet. What we would see is that line, those 1500 angstrom lines, shifted to 7500 angstroms, Z plus 1 times this. So ultraviolet light would appear as far red. And we need to take this into account when we're looking at different galaxies at different distances. This is a plot of the age of the universe as a function of redshift, and the model is based on the expansion of the universe as we understand it. Today, the universe is here, 13.8 billion years old. Suppose we're looking at that redshift 4 galaxy. Then we're seeing it as it was when the universe was less than 2 billion years after the Big Bang, because it's greater than 11 billion light years from us. At a redshift 2, we're looking at the universe when it was about a third of its current age. This was the period when there's peak star formation in the universe. At redshift 1, we're looking at the universe when it's something like half its current age, which is approximately when our sun formed 5 billion years ago. So here's a time scale with ages and redshifts. Recombination is when the first atoms formed, about 300,000 years after the Big Bang. If we look at cosmic noon, Z equals 2, that's when we have the peak star formation. This is the current day universe. What we're particularly interested in galaxy studies today is looking at this region around here, where we have galaxies that are very far away. They're just beginning to form. And so we want to look when the universe was about 1 billion years old. So that's all this region here. And you can see this cosmic web persisting today, forming new galaxies. So when we're looking with different telescopes, we can reach different regions. Hubble Space Telescope goes out to something like a couple billion years after the Big Bang. But if we want to go even further away, we need to go to the infrared, and that's where Webb comes in, and we're pushing to less than 1 billion years after the Big Bang. The Hubble deep fields in the north and south were imaged in 1996. Hubble was pointed at blank regions of the sky where there were no known stars or galaxies. So after long exposure, it turns out thousands of galaxies popped into view. This is looking at regions primarily about redshift 1. Galaxies that have high redshift often look peculiar compared to today's galaxies. So we look at the universe today, we see ellipticals and spirals. 9 billion years after the Big Bang, we see ellipticals and spirals. 5 billion years afterwards, not so much. They start to look rather odd. They're smaller because they grow over time, but they also have different shapes. So on the left, we see a census of galaxies in the deep fields where we have spirals and ellipticals, but we also see all these other unusual clumpy galaxies. We call the top ones chain galaxies. We think they're just a disk seen from the edge where we have big knots of star formation, or flying over them, they appear rounder, or they may have two main lumps of star formation and a lump and a little tail. We don't see galaxies like this in today's universe, in the regions around us, and therefore they must evolve into something else. And so the question is, how do they go from this kind of shape to shapes that are like what we see in the nearby universe? The ultra deep field was imaged in 2003 and subsequently with different filters over the years. And on average, it's reaching distances more than twice as far as the Hubble deep fields, but individual galaxies can be quite far away. There are 10,000 galaxies in this image. How big a piece of the sky is this? Take a needle, hold it at arm's length, and look through the eye of the needle. That's the piece of the sky that we're seeing. So we're looking at 10,000 galaxies in that little tiny piece of the sky. which is just, of course, a fraction of all the galaxies in the universe. Here's part of the ultra-deep field, and you can see a lot of interesting galaxy shapes. Let's zoom in on some of the distant ones, and here's what they look like. They're very odd. We don't have galaxies like this near us today. Clumpy galaxies in the early universe have huge nuts of star formation, and they're growing over time. So they accrete gas from the cosmic web, just protons, hydrogen gas streaming in, and that gas collects together, and if it's dense enough, then it can collapse and make new stars. But we can measure the disks in these galaxies, and they're very turbulent. They have motions that are 50 to 100 kilometers per second, instead of the gas motions in today's universe, where they're 5 to 10 kilometers per second. So in order to overcome those very high random motions, you have to have a lot of mass. You have to have high gravity to overcome it. And so that's why whatever forms is a very high mass clump, much bigger than the clusters that form in galaxies today. Let's go back to a simulation and zoom in on a piece of the cosmic web and zoom in on this area here. And this is looking at a galaxy that's growing at about redshift 2 in simulations. And if we look in more detail, if we could fly over that region, this is what the galaxy would look like, where this is color-coded for density, and the white and red regions are where they are densest. So this is where the stars are forming in these big clumps. And side view, we see a linear chain galaxy. So this simulation is matching the kinds of galaxies we see at about redshift 1 to 2. When did the first spiral galaxies form? We've done a survey of galaxies as a function of redshift and sorted them into different types. And it turns out most of the spirals appear when the universe was about a third its current age, at redshifts 2 or more recently. So here are a number of different spiral galaxies that are closer than redshift 2. This is a marker of when waves are able to ripple through the disk to create pinwheel patterns. That's when the disks settle down. They're less turbulent, and so the waves are able to manifest themselves. So here's our proposed evolutionary sequence. As clumps dissolve or migrate to the center, we start off with a clumpy galaxy with lots of massive star formation that eventually begins to settle down. As we're accreting more gas, there's more gravity in the disk, and so the disk shrinks a little bit, it gets thinner, and it radiates, and so the disk becomes less turbulent. And so eventually we have smaller star-forming clumps, and we end up with spiral galaxies. The Hubble frontier fields are looking at clusters of galaxies at redshifts between 1 and 2. So here are some galaxies. Let's zoom in on them. And sometimes there are surprises. If we look at this little piece, we see something that we call a little blue dot, something that we haven't seen before in our nearby universe. It turns out these little blue dots are about 100 times the mass of the globular clusters that are in our galaxies today. They are round, they do not have any extent beyond them, and so we think that they may be the precursors to the globular clusters that are in the halos of big galaxies. Possibly they were consumed by our galaxy, the outer parts is shredded, and what's left is this gravitationally bound core of old low-mass stars. Here's a distant cluster of galaxies observed with James Webb in the mid-infrared and in the near-infrared. And we see a lot of interesting things like gravitational lensing, which I think is the subject of another talk today. Here are some more distant galaxies, again with very peculiar shapes. Here are some candidate high redshift galaxies, redshift Z of 11.5 out to 14. And so to confirm this, you need to do spectroscopy, which I'll come back to in a moment. Here is the first image from James Webb, and it reveals some spiral galaxies between redshifts 1 and 3. They're a little odd looking, but they clearly have some spiral structure to them. They're intrinsically very red, not just because of the expansion of the universe, but because they have very heavy dust obscuration. When dust is blocking starlight, it preferentially absorbs blue light more than red light, and so a dusty region appears red. One surprise with this early universe picture is a massive spiral galaxy observed at a redshift 5. This galaxy is the size of the Milky Way. It's, again, got a rather chaotic spiral structure, but clearly a spiral. But it would have formed in the first billion years after the Big Bang. So does this negate some of the early cosmology simulations? No, it doesn't, because these are rare. We saw that dark matter randomly clumps in the early universe. And if we have a denser pocket, then gravity is stronger, and gravity dominates all of these physical processes on a big scale. So higher density means more stuff, and everything is processed more quickly. And so therefore you can get randomly, once in a while, a very high mass galaxy evolving very quickly. Another surprise are what are known as little red dots. These are less than 100th the size of the Milky Way. They're observed at redshifts between 4 and 9. There have been a couple of dozen papers over the past couple of years trying to analyze them according to their light emission at different wavelengths. It's not quite clear what they are. They may be supermassive growing black holes, and we'll hear more about black holes in another talk. Or they could represent extreme star formation. Or a recent paper suggests that they may be, in fact, a black hole that's embedded in an immense cocoon. One little red dot contains a confirmed black hole. The emission of it matches, of the region around the black hole matches what we would expect for a black hole. It was formed just 500 million years after the Big Bang. It's at a redshift Z of 9, and it's 300 million times the mass of the sun. Here's a spectrum of a high redshift galaxy. Again, it's through the spectrum that we can confirm its distance. Here's the galaxy in several different filters, and here looking at various emission lines. And according to the redshift, then we can trace how far away the galaxy is. Here's another massive galaxy observed at a redshift 9, different filters, and with spectroscopy showing that it's this far away. It's got 1 billion times the mass of the sun. So when we're looking at these distant galaxies, when we see these various emission lines in the gas, that's again telling us something about the star formation history, because these elements only could have come from previous supernovae, high mass stars that process hydrogen into helium, into heavier elements. As they supernovae, they make even heavier elements, and that is what gets dumped into their surrounding gases in the galaxy. So the fact that we have neon and oxygen in addition to hydrogen means that there's already been some high mass stars that have formed and evolved in this galaxy at 13.1 billion years ago. So just less than 1 billion years after the Big Bang. Here are several other galaxies in this deep image, and you can see these different lines, hydrogen and oxygen, with different redshifts, because they're 11 billion years ago, or 12, or 13 billion years ago. The most distant galaxy that's confirmed so far is at a redshift of 14.3, which is less than 300 million years after the Big Bang. So the formation and evolution of galaxies is becoming more clear as we continue to push the boundaries of observation and theory. Here we have Hubble looking at galaxies near us, out to the Hubble Deep Field and the Ultra Deep Field. We've got the frontier fields here, push even further to within the first 500 million years after the Big Bang, and James Webb is looking at those very first stars and galaxies. So as we continue to explore the universe, we are all together under one sky. So keep that in mind, and good luck with your studies. Thank you for your attention. And now I'll be happy to take any questions as time allows. Thank you.
So we will, whoops. Yes, I'm back. So we are now going to switch out the pre-recorded Deborah against a live Deborah. There is a live Deborah. Hold on. Hi, Deborah. Thank you. Also, not least, thank you for being patient with what is shaping up a little different than planned.
I appreciate everyone who has stuck with us through this difficult global phenomenon.
Big thank you to the 57 who made it. Big thank you to everybody at the OAE who has been rotating very quickly behind the scene, trying to get the word out. So we'll see how the situation develops further. We'll try Ring Central after this is over, see if things have been restored. If not, then please, if nothing happens on Ring Central, please keep either this or the OAE YouTube channel in your eye, and then we'll keep an eye on either of the YouTube channels, either this one here or the one by the OAE itself, and then we'll continue improvising. All right, but continuing in the regular program, first of all, thank you, Deborah, for a really nice overview right until the last final results with the little red dots. My first question is a personal one. You have been in the Galaxy game for quite some time now. Is it currently the speed of research currently picking up, or have you thought this throughout the decades that you've been doing this, that it's always getting better and better and more?
Oh, for sure. It's always getting better and better. I've been observing galaxies for over 50 years now. And I was the lone man on the mountain back in the day with photographic plates. And it was a big transition to go to CCDs in the 80s and 90s. IRAF came along. And then everything changed once we got Hubble. And so, yeah, I think pushing the boundaries, and now with Webb, I'm on several large teams, and that's one thing that's different. It's not an individual astronomer or 2 or 5 or 10. It tends to be big teams that might be 50 or 100, a couple of hundred people to work with massive data sets. So whereas I used to look at individual galaxies one by one, thousands of them, but not millions of them, which people are doing today with all kinds of wonderful methods that I don't even know how to do. So I'm amazed on these big teams to see that particularly the young people, this was true at every stage. The younger people always knew more than I did about the latest techniques and would have to show me what to do. So I'm seeing that now, and I think it's wonderful to see how everything just keeps exploding. It's very exciting. I must say I miss being on the mountaintop, which you can still do, but not as much. But it's just glorious that the data are so much better now and so much more extensive.
How do you think the role of individual astronomers has changed? Because the people who do or do not get the permanent positions, to sort of mention the ultimate currency in a scientific career, those are individuals. I mean, we are not yet at the stage where teams get hired as teams, right?
That, I think, is one of our big challenges, is to make sure that everyone on a team has a role to play, and that role gets acknowledged in some way, that their skills stand out. And I do think that's a challenge. If you're one of a couple hundred and you played a role in clearing out the cosmic rays on the data set, and someone else is measuring the masses, looking at spectral energy distributions, things can get very specialized. And so it's important for young people in particular to be working on lots of different aspects on a big team, or otherwise I think you could get lost in the shuffle and your role would not be clear. So I think that's going to be a very important consideration moving forward, to make sure that the individual still stands out in some way. I don't know exactly how to address that, but it's a real issue.
I mean, I'm sort of outside of research astronomy, being in education and education research and outreach. So I look with great interest to also to the various generations of the few generations that I'm looking at now. And it seems to be until very recently that there were still at least skills within teams, maybe not cleaning cosmic rays, but I know at least one astronomer who basically, I think, made her career on getting to know ALMA very well, very early on, and then being in very high demand as people struggled with this very complicated instrument. So,
oh, absolutely.
There still seems to be a way to distinguish yourself, but it seems to be a strategic choice, right? I mean, if you just, it seems that the people who make it are not the ones that just drift along, but the ones that sort of see which are the ones where they can have a personal impact, or the
Well,
ones that
that's right.
just have the ideas that happen to become important.
That's right. And typically the teams I'm on, the papers sort of rotate through with different people as first author, looking at their particular area, looking at embedded star clusters, or looking at details of spiral structure or the dust grains or that sort of thing. So I think it's important that particularly younger people on a team get a chance to lead a paper so that they can really stand out in that way.
We actually have one question that goes a little bit towards what you were saying earlier. I'm just going to put it in here. How confident are you that working together with all nations across the world has a future? And if you're not too optimistic, how can we find our way back to that state of affairs? That's the
Yes,
big one, isn't it?
that is a very important question. When I was very young and very naive, one of the appeals of astronomy, besides the visceral feeling I had from looking at the night sky, was that it was far removed from the problems on Earth. How naive I was. I didn't realize that so much of astronomy depends on government funding, for example. We're in a really tough situation, I think, when people begin to question science. And I think international teams must continue. I think that countries may ebb and flow in how much money they invest in science, but I think that most people recognize the value of real science, and whether it's astronomy or any other science field, and that ultimately it improves economies. If nothing else, doing science improves economies. Half of the economic development in the United States since World War II has come directly from scientific advances. So I think that many people still believe that that's true. I think that things are a little tough in some areas of the world right now, and but I think the international collaborations will continue because scientists still want to communicate with each other and work together, even if governments seem not too interested at times.
Yeah, I mean, it is true. Yes, it is true that the economic benefits are there, but even governments that purport to be pro-economy, looking in your direction, I apologize, not you
Yes.
personally, but
Yes, no, it's I can't be more sad about it. But I do believe that science will go on because we all still want to work together. And yes. I see another question. Current big
yes.
unsolved questions. Yes, getting back to astronomy. I think that
Let's first read the question. In your opinion, which are the current big unsolved questions in galaxies in extragalactic astronomy?
I think the questions change practically every week with these new discoveries. Yeah, okay, we see big galaxies early on in the universe, and first people said, "Whoa, that can't be. How can that be?" But okay, that's fine. There's a few, but as more and more start to be discovered, then it does mean we need to tweak our details about cosmology. So, so I think just understanding what's happening in the first half billion years is the key area right now to figuring out what galaxies are doing. I think we understand a lot about local galaxies and we understand a lot about star formation. There's still a lot of unresolved details, but I think the big picture of exactly how it all gets going is a real important focus today in terms of extragalactic astronomy.
And the tools that are going to help us, I mean, James Webb, obviously. I mean, that's what James Webb was designed
Absolutely.
for.
Webb and ALMA, got to have the gas, got to understand the dust, and certainly, yeah, okay. So someone says, and beyond dark matter, yes, certainly trying to understand exactly what dark matter is doing and what it is, I think is critically important. But just understanding the baryons in the universe, I think a big push today that now that we're going to have surveys such as the Rubin Observatory, where we get a very large scale picture around individual galaxies and clusters is going to change the way we think about gas. We can see in the simulations that the cosmic web is feeding the galaxies, but now we can start to observe the envelopes around galaxies and around clusters of galaxies in a way we couldn't before without such wide field coverage. And I think that that will be very important too.
I remember that for me, that was sort of one of these moments where things sort of turned on its head when you look at simulations like the Next Generation or similar, and suddenly what you used to think of as galaxies is just sort of not even the icing on the cake. It's sort of the icing on the icing on the cake. It's sort of the little star thingies on top of the baryonic gas on top of the dark matter. So that's it's a fairly that was sort of a mind-blowing moment for myself when I sort of, I mean, because there's just so many facts and things and methods to learn, right? And it takes a lot to change the big perspective. So when you sort of work your way through very slowly and learn this and learn that and learn that, and then suddenly sort of it flips on its head. That's
right. Exactly.
That's the kind of thing that makes this fun also from a teaching perspective, because I mean, I think many teachers in particular, when it comes to astronomy, those who are educational stakeholders, at least half of the fun is that you get to learn yourself about.
Oh, absolutely. Absolutely. My lectures changed every year in astronomy as new things came along.
Yes, and that's not at all a given, right? I mean,
right.
Their introductory lectures tend to sort of be the basics of the basic and the basics, and if the discoveries that were made last year make it into the introductory lectures, that's saying something.
Oh, absolutely.
All right, so we have to come to a stop. Thank you very much also for your time. It was much longer than we had originally asked you, so thank you for staying with us. Thank you to everybody who's here for staying with us. We have noticed that Ring Central, our original event platform, is apparently back online. So if you look at the comments now, Haus der Astronomie has posted a link. Those of you who came here from who were already registered, please go back to Ring Central now. If you've drifted across this YouTube channel without being already registered for the workshop, please follow the link in the comments, the one that is events.ringcentral.com. It's a free online event. It goes until Friday, and there's going to be 3 additional sessions on galaxies. First of all, on the dark side of galaxies, then on the Milky Way, where we have a really nice lineup, including Michael Perriman for Gaia, and so on. We have for the from the survey side, we have Karen Masters with an interactive workshop. We also have Cecilia Scorza with an interactive workshop on how to teach about galaxies. That's the galaxy. I think that's the galaxy history session, which is the last one, where we have, among others, Annalisa Pilipic telling us about the state-of-the-art simulations. So if you're interested in galaxies or beyond in astronomy education, hopefully lots of interesting content. So follow the link, and we are now going to close rather unceremoniously because I didn't get to take the outro video with me. So I think we'll just wave into the camera, and I'm going to stop the stream. Thank you again, Deborah.
Thank you, Marcus. Thank you, everyone. Good luck.
Bye.